Welcome to the 40th lecture in this open course on diffusion in multi-component solids. In this lecture, I shall derive the relation between atomic mobility and diffusivity. In this process, we will get introduced to thermodynamic factor. In the later part of this lecture, I will talk about diffusion under external driving force and derive the Nernst-Einstein equation. I shall also illustrate the application of this equation to the process of electromigration, that is, the process of diffusion under electric potential gradient. So, last class we discussed why chemical potential gradient is the fundamental driving force for diffusion. We also derived the equation for diffusion flux in terms of chemical potential gradient of a component and the chemical potential gradient of vacancies. So, flux of a component is related to the chemical potential gradients of different components through the kinetic coefficients Lij. So, for example, in binary we can write Ja is equal to minus Laa dou mu a by dou x minus Lab dou mu b by dou x in a binary AB solution. If the chemical potential gradient of vacancies is assumed to be 0, that means if there is no net vacancy flow, then this cross kinetic coefficient term Lab is absent, and we can write Ja just in terms of dou mu a by dou x as minus La times dou mu a by dou x. La here is the kinetic coefficient that relates the flux of component A with the chemical potential gradient of A. We have seen this La is given in terms of d star times Ca over Kt. Here d star is the Einstein's diffusivity, which was given by 1/6 gamma lambda square. This is also commonly known as tracer diffusivity, and d star essentially characterizes the self diffusion or impurity diffusion under no concentration gradient or a very minute concentration gradient respectively. Now, La is the kinetic coefficient. What is the physical significance of this? The physical significance of La can be understood if we again take a look at the equation for flux, and if we rearrange the term, La is nothing but minus Ja over dou mu a by dou x, and minus dou mu a by dou x here is the driving force. So, the physical significance of La is that it is nothing but the diffusion flux of a component per unit driving force. Many times we come across the term atomic mobilities. What is this atomic mobility and what is its relation with the kinetic coefficient? So, let us try to look into it now. A few classes back, if you remember, we have seen the flux can be given as Ja is equal to Ca times Va, where Ca is the concentration of A and Va represents the mean velocity of atoms of A. Now, this velocity can be considered to be proportional to the driving force, and it is related to the driving force through the term called mobility. So, we can write V A is equal to minus m A times dou mu A by dou x. So, negative dou mu A by dou x is the driving force here, and m A is the constant of the proportionality, which is called as atomic mobility of A. So, similar to the kinetic coefficient, if we rearrange, we know the physical significance of the term mobility. So, just like kinetic coefficient was the diffusion flux per unit driving force, mobility is the velocity per unit driving force. So, m A is nothing but the velocity per unit driving force. So, if we substitute back for V A in the equation for J A, we get J A is equal to minus m A C A dou mu A by dou x, but this is simply minus L A dou mu A by dou x, and so L A is simply m A times C A. So, the atomic mobility or kinetic coefficients, they represent essentially the same quantities, they are related through the concentration C A. But the mobility is more general term, and mobilities are also used to store the databases for interdiffusivities and diffusivities. And so, let us try to establish the relation between the mobility and the diffusivity terms that we use. Since we know L A is equal to d A star C A by R T, if we consider a mole, then we can replace K with R, and so we can write M A is equal to, that should be d A star by R T, or d A star is equal to m A R T. So, the tracer diffusivity of A is related to the atomic mobility of A through the simple relation d A star is equal to m A R T. Again, this relation is applicable if we are considering a binary system and we are neglecting the net vacancy flow, because if the net vacancy flow exists, then we have to also consider the cross kinetic coefficient terms, which means we also need to consider the cross mobility terms. Since we are using a single mobility to represent a single component here, this is valid when there is no net vacancy flow or the chemical potential of vacancies is 0. Now, d A star is the diffusion coefficient in negligible concentration gradient. What happens when there is concentration gradient present? In that case, we talk about interdiffusion or intrinsic diffusion, or commonly it is also referred to as chemical diffusion, which is characterized by chemical diffusion coefficients. So, let us see the relation of mobilities and the chemical diffusion coefficient terms. In presence of concentration gradient, we can write the equation for flux as J A is equal to minus d A dou C A by dou x, which in terms of chemical potential gradient is written as minus L A dou mu A by dou x, or in terms of the atomic mobility it is written as minus m A C A dou mu A by dou x. Now, I need to relate the interdiffusivity term d A with the mobility m A, which means I need to express this dou mu a by dou x term in terms of dou C a by dou x. One point to be noted here, when I am writing this equation here, I am considering the diffusion flux with respect to a frame of reference which is fixed to a lattice plane. This is also referred to as Kirkendall frame of reference, and we will talk about this frame of reference in more detail later. But at this point, remember that I am talking about the frame of reference which is fixed to a lattice plane. It is also referred to as intrinsic diffusion, and this diffusivity dA is the intrinsic diffusivity of A. So, we know mu A can be written as mu A0 plus RT ln AA, where mu A0 is the chemical potential of A in its standard state, and typically the standard state is taken as pure A, and so mu A0 refers to the molar Gibbs free energy of pure A in its stable state at the given temperature, which should be constant, and AA is the thermodynamic activity of A at the given composition. Now, dou mu A by dou x can be written as dou mu A by dou C A times dou C A by dou x, and we know C A is equal to x A over V m, where V m is the molar volume and x A is the mole fraction of A in the solution. So, if we assume molar volume to be constant, this can be written as V m times dou mu A by dou x A times dou C A by dou x. Now, if you differentiate mu A with respect to x A here, we get dou mu A by dou x A should be equal to R T times dou ln AA by dou x A, and AA is nothing but gamma A times x A, where gamma A is the thermodynamic activity coefficient of A and x A is the mole fraction of A. So, this can be written as R T times dou ln x A over dou x A plus dou ln gamma A over dou x A, and if we substitute back for dou mu A by dou x in the equation for J A, we get J A is equal to minus M A C A times V m times R T dou ln x A by dou x A plus dou ln gamma A by dou x A times dou C A by dou x. Now, C A V m is again nothing but the mole fraction x A, and if we take this x A inside, these derivatives we can write as dou ln x A by dou ln x A and dou ln gamma A by dou ln x A. So, the first one should be 1, and so we get J A is equal to minus M A R T times 1 plus dou ln gamma A by dou ln x A times dou C A by dou x, and this is nothing but simply minus d A times dou C A by dou x. So, we compare these two sides, we get the expression for intrinsic diffusivity dA in terms of the atomic mobility m A, and they are related as dA is equal to m A R T times 1 plus dou ln gamma A by dou ln x A. So, the intrinsic diffusivity is related to atomic mobility through this factor dou ln gamma A by dou ln x A. When the solution is ideal, gamma A is 1, and so dA is simply equal to MART. But in case of non-ideal solution, dou ln gamma A by dou ln XA will have value other than 1, and so we need to take into account this factor, and this factor is commonly referred to as thermodynamic factor. We denote it as phi. Phi is equal to 1 plus dou ln gamma A by dou ln XA. Based on Gibbs-Duhem equation, it is also easy to show in a binary system. This is same as 1 plus dou ln gamma B over dou ln XB, and so dA can be written as MART times phi. Now, if we are considering a dilute solution, we know Henry's law will be followed, and so gamma A will be a constant. And again, when I am considering dilute solution, dA is nothing but dA star. So, dA star is equal to MART. So, the tracer diffusion coefficient dA star is simply equal to MART. This is what we have already derived. Again, this equation we have derived for a binary system. If we consider multi-component system, and if we consider net vacancy flow, which is also called as vacancy wind effect, then we have to take into account the cross mobility term, and the relations will be more complicated. So, let us now restrict our discussion only for binary and in absence of net vacancy flow. So, these relations give us the interrelations between the chemical diffusivity terms and more fundamental atomic mobility terms, and these relations are important because they help us to relate the information that we obtain experimentally, which is most of the time the tracer diffusivity or chemical diffusion coefficient, to the more fundamental coefficients, which are the atomic mobilities or the kinetic coefficients. So, we have considered the diffusion under chemical potential gradients. We will now look into what happens if there is an external driving force present and the diffusion is occurring in presence of an external driving force. What type of external driving forces can be present? It can be an electric field, which is nothing but the gradient of electric potential, or it can be a stress field, which is nothing but the gradient of strain energy. It can be the gradient in temperature, and so on. So, let us try to look into the diffusion when external driving force is present. Earlier we have seen there are two contributions to any diffusion flux term. So, if we write JA, the first contribution is from the Fickian term, which is nothing but minus dA dou Ca by dou x, and the second contribution is from the drift, which is written as Ca times V. Ca is the concentration of A, and this V refers to the drift velocity. Now, let us consider the strain energy driving force which may be present. For example, consider the diffusion when strain energy exists in the alloy. So, we have to increase the Gibbs free energy of the alloy by appropriate amount equal to the strain energy, and we can write mu A equal to mu A0 plus RT ln AA plus E. This can be easily seen if we draw the Gibbs free energy of a solution versus composition curve. So let us say on x axis we have xb, so left y axis is xa equal to 1, y axis we are denoting Gibbs free energy of solution, and the curve may have a nature something like this. In the absence of the strain energy, if we want to find out the chemical potential, we draw tangent to the curve at the desired composition, and the intercept on xa equal to 1 axis yields the chemical potential of A, which is nothing but mu A0 plus RT ln AA. Now, in presence of the strain energy, this curve will be shifted up and at the same composition the difference would be E. So, if we determine the chemical potential now, it has increased by amount E, and so we can write mu A equal to mu A0 plus RT ln AA plus E. So, if we write the equation for JA now, it will be minus MACA dou mu A by dou X, and so if we follow the previous steps, then it will be easy to show that JA is now equal to minus MART phi dou CA by dou X minus MACA times dou E by dou X. If we substitute for MA, because dA is equal to MART phi, so MA is equal to dA over RT phi, and we can write JA is equal to minus dA times dou CA by dou X plus CA dA times minus dE by dx over RT phi, and this minus dE by dx is nothing but the driving force, that is the gradient in strain energy, which acts as the driving force, which we denote as F. Now, if we compare this equation with the equation that we wrote earlier here, we can see the drift velocity is nothing but dA times F over RT phi, or we can in general write V over dA is equal to F over RT phi. If we consider a dilute solution or an ideal solution, this takes the form V over dA is equal to F over RT, and this is the well known Nernst-Einstein equation. What is the significance of this Nernst-Einstein equation? If we go back to the equation for flux here, for defining the Fickian term, of course we need the diffusivity dA, but to get the drift term also we need the diffusivity term dA. In other words, or in terms of Nernst-Einstein equation, the drift velocity is also governed by the diffusivity dA or the mobility ma, in addition to the nature of the driving force F, which is obvious because both the Fickian flux as well as the drift will be fundamentally driven by the atomic jumps, and so atomic mobility would essentially occur in both of them. Again, I would like to point out, when we derive this equation, I am considering the binary system and I am neglecting the net vacancy flow, that is mu v, or the chemical potential of vacancy, is assumed to be 0. Now, let us look into the diffusion that occurs under a specific type of driving force, which is industrially very important, and it is the diffusion under electric potential gradient. It is also referred to as electromigration. So, when I talk about electric field as the external driving force, F is essentially Q star times E. The electric field is nothing but the gradient of electric potential minus dV by dx. Now, Q star here is the effective charge on the diffusing species. For ionic compounds, this effective charge will be essentially the charge on the ions, but in metals it is not actually the charge on the metal ions, but these effective charge values have to be determined experimentally. So, if we want to find out the drift velocity in presence of electric field or drift velocity for electromigration, we can use the Nernst-Einstein equation, which tells me V over dA is equal to F over RT, and F here is nothing but Q star times E over RT. And so, if we write the equation for J, which is minus dA times dou Ca by dou x plus Ca times V, so Ja is equal to d minus dA dou Ca by dou x plus Ca dA Q star over RT times E. So, this tells me that the diffusion flux of A is governed not only by the concentration gradient, but also by the electric field E. And it also tells me that even in absence of any concentration gradient, the species can experience large diffusion flux if the electric field is high. Now, this is very important. In most of the semiconductor chips, pure copper or pure aluminum is used as interconnect material. With ever decreasing feature sizes, these interconnecting paths of copper or aluminum have very small dimensions in nanometers, at which the electric field is very high, and so there will be the flux of atoms even in pure copper or pure aluminum. Now, this is not desired, because if the atoms diffuse from one end to the other of the conductor, there will be accumulation of vacancies on one end, which will lead to formation of voids and subsequently to the failure of the connector. On the other hand, the atoms are accumulating on the other side of the conductor, and it may lead to undesired growth, and so it may lead to short circuiting. And so, it is very important to control this electromigration in semiconductor chips, and there it is essential to work with the flux equations like this. So we have seen the equation for diffusion flux when both the concentration gradient and electric potential gradients exist. Now let us try to look at physically what happens, why there is a diffusion flux even when there is no concentration gradient, or when both concentration gradient and electric potential gradients are present, why there is a drift term associated with the electric potential gradient. So let us try to look at it. So consider this sample. I have shown different atomic planes here. In the absence of any electric potential gradient or any external driving force, these atoms are continuously vibrating and their jump frequencies, as we have seen, in forward or reverse direction are same. So gamma plus and gamma minus are same. Now consider there is an electric potential gradient existing from left to right as shown here. So the electrons are flowing from right to left. Now as the electrons are flowing, they are colliding with the atoms, and in this process the electrons are transferring their momentum to the atoms. Because of this, the jumps of atoms are biased in the direction of flow of electrons. So there will be more jumps per unit time from right to left as compared to from left to right, even when there is no concentration gradient. Because of this, gamma minus, that is the jump frequency towards left, is not same as gamma plus, that is the jump frequency towards right, and in fact gamma minus will be greater than gamma plus. Of course, there will be also an effect because of the interactions between the charges, because electrons have negative charge and the ions will have positive or negative charge. But the effect because of momentum transfer from the electron is much more significant, especially in metals. In ionic compounds, the momentum transfer is less and the effect because of the charge interactions is more, but in metals the effect because of the momentum transfer from electron is more, and because of this the effective charge Q star that we have denoted here in this equation, this Q star is not exactly same as the valence of the atom. In fact, it comes out to be much higher than the valence. So for example, if we see carbon in alpha ion, effective charge for carbon diffusion in alpha ion is -12, whereas that for hydrogen in copper the Q star is -20. So as you can see, this effective charge is much higher compared to the valence, and that is because of this momentum transfer, the bias in the jumps because of the momentum transfer from the electrons. So this is the nature of electromigration and why there is a drift as we understand physically. Now there are various other driving forces also. We will not talk about all of those. We have seen the electric potential gradient. In the next class I will talk about non-ideality as a driving force. For this class we will stop here. Thank you.